Okay, I'm not giving a shout out to Mason Dick. He's not here today, and he won't be listening to this. Welcome to Calculus in the PM. 7.4, exponential growth and decay. Separable differential equations. Now, I've talked about separating the differentials or the variables, separate the variables. So, this will build on something. Now, if we have a differential equation like this, where we say dy by dx is equal to something with a y in it, like y squared times x squared, g of x, some function of x, x plus 5, whatever. We call them separable. We could separate the variables by writing it in this form. Move the y's to the dy side. Then think of the dx as zipping up there and keep the x's on the dx side. So we put all the y's and dy one side, all the x's and dx on the other side. If you have a constant, like a 5 or plus 3 or something, you could decide if you wanted it on the y, the x, times 5 or so. The solution is found by anti-differentiating each side with respect to its isolated variable, y or x. Now, let's just do an example and we'll see. So dy by dx is equal to x squared, y squared. So this looks like something you would have gotten as an answer from a implicit differentiation. There we go. But then we have specific conditions when y equals 3 and x equals 0. Evaluate. Solve for y. First thing we have to do is, I can't undo this the way it's written because there's y's in here. Undo as in integrate. So I separate. I move the y's to the left, and I keep the dy on. So dy on this side, and I'm going to divide by y squared. Now, just to show that I'm dividing it over, I'm going to put 1 over y squared for a second. Is that the best way to think of this, though, if you're doing an integral? Okay. But you see where I got that from the other side, the right-hand side. I'm going to write it as, though, even though I'm dividing by y squared, what's the best way to write that? To do an integral, or to do differentiation. -2. So, I'm really thinking of it as divide by y squared, but I'm going to write it, which means the same thing, y to the -2. X squared stays on this side, but I'm moving the dx from here to there. Okay, once I do that, I've separated the variables. Make sure you do that. How do you undo differentiation? Integration is the key, right? So, you guys got me on this? Got it? Okay, integrate both sides. And this is exactly what yours. Yeah, okay, you see. Question 4 or something like that. Start at page 2. It'll be like that. So, what is the antiderivative in this case? Y to the -2, the blue stuff. Would have come from something with a slightly higher exponent. So what would the exponent be? Y to the up 1, -1, with a -1 over 1 in front of it. So just minus sign, right? Are we good with that? Okay. Now, I'm calling it an antiderivative because if I wanted the indefinite integral, I'd say plus c on here. And it really is, but I'm going to just write that in green and not include it. Don't write this down, you'll see why. They don't cancel though. I'll maybe call it C1. But I know what you're thinking. X squared must have come from something with an x cubed. The easiest antiderivative I can think of is 1/3 x cubed, right? If I want to do the indefinite integral, it's a different concept. They don't cancel out because this side could be plus 3, this side could be minus pi quarters, right? I don't know what the... But do we all agree that, and this is why you're not doing this, Don't write the green. I could just group these, I could subtract this over, but whatever you have, you've got to group these constants, you could have moved it to the left or to the right. Either side you could include it on. They do not cancel out.
They can be combined.
But they could be combined for one constant. So let's just say it's one constant on one side. Choose a side. Typically I use the right-hand side. Usually I put it on the side with the x, but that's, it doesn't matter which side you put it on. It has to be on one of the sides. Okay? So there's the reason why we have it like that. Okay. This doesn't really solve our problem. We got to solve for y. And y, we have 1 over y, negative 1 over y, right? We understand what that means. But we got to find out, how do we find out what that constant is? Because we can get the particular solution. Yeah, y equals 3, x equals 0. That'll give us the value of the constant for those conditions. So, y equals 3. So this is really negative 1 over 3. Y to the negative 1, right? 3 to the negative. Okay. And then I toss in my x equals 0. 1/3 times 0. I'm going to write that down just to show you. Okay. I think you can quickly see that c is negative 1/3, right? Now let's go backtracking again. The particular solution for this. I can do this because I need to make space. Maybe you didn't fill up yours hopefully as much as I did. So, it's sort of like my second column here. The particular solution that I want. And why do I say particular? Because the general solution is the one with, you know, this constant in here. These particular conditions are met, y equals 3, x equals 0. That's why particular. Anyways, we've used the term before. We now use x and y. We have an actual number for the constant, of negative 1/3. So I'll just start back, and I'll use one color now. We're going to call this negative 1 over y equals 1/3 x cubed subtract 1/3. Okay? Now I have not solved for y, but that's not too difficult. What do? We don't need to sub in, we're solving. Because now this is the particular solution. We've already subbed in for x and y, and that's how we got this constant. Now, if we just subbed in for x and y now, it should come out to be 0, like both sides should equal each other, right? And it would. So that doesn't give us anything. We want to solve for the variable y, a function of x. So we just flip, right? Some reciprocal. Is this the best way to, is this the best form to flip though? If we're going to flip this side, fair enough, we got y over. I think we should get this, look at this, 1/3 x cubed minus 1/3. Let's get this all as, if you're going to use a reciprocal, get the whole side as a fraction.
X thirds subtract 1.
Yeah, x thirds subtract 1. Aren't these both out of 3? So I'm going to have one big. So what I'm saying is that the same expression? That's what I'm trying to say. Apology accepted. No need to apologize. True that. Now, if I flip, I got y on the top. Transferring the negative side left to right, multiply both sides by -1, whatever you want to think of it. I'm going to do that all in one step. This ultimate destination. Final. So I just had to tune Tristan in back onto the video, Mason. He's not going to watch this. If y changes at a rate, Now this is important here. You'll see a sentence something like this, right? If y changes at a rate proportional to the amount present. Now you'll see some variation of this and you'll come across it. That is, if dy by dt time is equal to some constant times y, the variable, ky. And if y is equal to y naught. Not, y naught, y zero. You'll often hear people refer to time zero as t naught or y naught. It just means y zero. You'll hear me. When time is zero, then y equals y naught or y zero, e k to the t. Huh? This is a whole bunch of stuff. What are we talking about there? Because it's almost like this is a, well, basically, if this, then this is the solution. Now, you don't have to memorize this, but it comes up often enough that you'll see it, and then you'll be like, you'll do it instantaneously. The constant k is called the growth constant. If k is greater than 0, so 3, 2, whatever. Or the decay constant if k is less than 0. Not negative, though. We don't tend to. We're talking like between 0 and, did I say less than 0? Yeah, negative. Sorry, my mistake. I was thinking of a different thing. Yes, when it's negative. Okay, my mistake. Now, we're going to do a little work underneath here. Show you what I mean. Starting with that original circuit expression, dy by dt. Ky. Where does this y equals y naught ekt come from is really what I'm trying to do. How would you solve this differential equation? You've got to separate the variables. So where does the y go? To the left side. The dt to the right side. And k is just a plain number, like it'll be 5y or something like that. Okay, ky, 5y, or 13 decimal 7. So I'm going to separate the variables. When I separate the variables, how do you solve this solution now for y? Differentiate, I mean, opposite of that. Integrate. Okay? So that's the next thing you do. Now, this is one of your memorized ones. Y to the negative 1, or 1 over y. What's the antiderivative there?
ln y.
Natural log. But we're going to make sure we say it's the absolute value. So this side is the natural log of y. Now, depending on your situation, you might be given a scenario where y has to be greater than 0, and usually it is. So you may or may not need to include those absolute value brackets. Include them with me. Now, the other side, remembering that this k is the number 5 or something. It's a constant. Question? Or is it the sound that you're wondering about? Yeah. Not a lot I can tell you about. What's the integral there? If this was 5t or 5 dt, what would the
kx.
not x though, t.
kt.
Kt. Yeah. So if this was 5t, the derivative of 5t is the number 5. Kt, the derivative of kt is k. So kt plus some constant, right? Now, do you guys see where this all comes from? Could be on either side of the constant. You're right. But how do you find the constant? Tells us here we're going to use if y is equal to y at time 0, y naught, when t equals 0. Let's plug this in here, and this is where this, you'll see. So then we use that little, we're going to plug in time equals 0. And we call the matching y value. We don't know what it was, the starting y value, but we're going to call it y of 0. So the natural log k times t, so k times 0, I'll put that in here. So what is the constant, obviously, then? Constant is equal to natural log of whatever value you have there. Now, I'm going to drop the absolute value of things, because you would know you'd have a starting condition. You know, at time 0, the population growth rate is whatever. You'd know whether it's positive or negative. So you would have to make a decision, but just the natural log of the initial y condition. That's what that means. Now this is a general recipe to solve an equation. I'm going to go on here. We have to now solve for y now that we have the constant. So basically we're taking this expression here. Okay? I'm only going to change colors just so you can differentiate one line from the other. Not differentiate as in math, just tell the difference. The natural log of y. You'll know whether or not that's appropriate to drop. Kt plus, I'm replacing c with the natural log of the initial value. Why not? The whole reason why I did this is now we can solve for y. How do you undo a log? What's the opposite operation? It's the exponential function. You guys, I'm pretty sure, he brought it up, so I think he knows what he's talking about. But let's just think back to this. Log base 10, I'll just do one of these. Log base 10 of 1,000 is equal to what? No. Like this is red, it's not to do with e's or anything. What's the answer here? 3. 10 to the what? Gives me 1,000. 10 to the 3 gives me 1,000. Now, the same information, 10 to the 3 equals 1,000. Just rewritten differently, right? You see how this gets? Okay. What I am saying is, if I had this expression, this expression, now I'm going to erase this all after, log base 10 of 1,000. And I said, how do I get rid of this? I'm just creating a simple problem, but just, would it make sense that if I said 10 to the log base 10 of, I change it to 100 here, 1,000. What's that going to simplify to? Just take a look at this and think about it. This red. It's going to be 1,000. Why? It undoes it, right? Like, do you guys follow how? Okay. They're opposites. You said it's going to be 1,000. Did you say it's going to be 1,000? Yes. Okay, good. In a sense, and it's not because this cancels this. That's not the right way to think about it, right? But they're inverse operations. They don't cancel like as in fractions or something like this. But you can clearly see right away that this, I'm on the wrong pen here, this expression here is the same as 3, right? So you'd say, well, that's 10 to the 3. 10 to the 3 is 1,000. It really just turns out whatever's here is what's left over. Now, I did all that to come back to this. So, maybe I'll leave it on there. I'll just move it over a bit. Okay, back to the green. So we take e to the everything, right? You guys all good with this? So e to the natural log of y is just y, right? I'll show it though, but I wouldn't normally. I just go to a straight up y. That means I have to take e to the whole side here. I'm showing it like this, full steps. Make sure that looks elevated, like the whole thing is the exponent. Because what happens is people get sloppy. They start writing this, and then by the time they get to plus ln of y, they write it full size. And then they get confused about what's in the log and what isn't. Or what's, I mean, in the exponential function and what isn't. Okay. What do you know when you're adding two exponents? What do we call that? You guys, it's multiplication. That's the operation. X squared times x cubed is 2 plus 3. Well, this is sort of like that 2 plus 3 step. We're going backwards, though. E to the 2 plus 3 is really the same as e to the 2 times e to the 3. In this case, first of all, I've brought up too many things at once. My mind's just racing. The left side is y. I get so excited when I do this stuff. Okay. Now I'm talking about this. E to the kt times e to the natural log of y initial. Y0. Why not? Now I know Schwab followed me on that step. Why not, eh? Why not, why not? Hey, what is the e to the natural log of y naught reduced down to? It's just y0, right? Okay, I'm going to move that in front though. The initial term, y0, e to the kt. Now, this is the result that we talked about here. Now, you would never spend this much time doing this. But it always comes down to that, like I've stopped and I've explained as I went through. I'm going to just read over this part. You guys take time to read over this. I'm going to stop the video though, no use while I talk about this. Take your time to read it. We'll just try these problems. These are problems you could have done actually beforehand if you have the end formula, but you know about this. Suppose you deposit $500, so that's your amount at time zero, A0, that pays 5.3% interest. How much money will you have after 4 years if the interest rate is continuous, if it's monthly? Really doesn't, you'll learn that that doesn't really make you a heck of a lot more money, it makes you some. So let's just take a look here. We're talking about this. Right? So if we do this, after how many years? 4 years. So that's the continuous interest, it's $500. E to the, now the rate as a decimal is 0.053 divided by 100. And the time was 4, wasn't it? Yeah, it was 4 years. If you put that in your calculator, and don't worry, I'll do it for you. $618. And 7 cents. Now, AP, get used to doing 3 decimal places, but since we're talking money, I'm going to stop at 2 decimal places. Because that makes dollars and cents a month. Otherwise, just assume 3 decimal places. Now B, what if you only compounded monthly? That's 12 times in a year, right? A, after 4 years, would still be, now we're using this formula here. The 1 plus, that's the one you've used before. So $500 times 1 plus the rate 0.53 over 12 compounding, 12 times in a year, and 12 compounding periods times 4 years. If you enter that in there with 48 as the exponent. 1770. So what this tells you is that compounded once a month compared to compounding every instant, more than every second, it grows you a whole $1 after 4 years, really. Not even, actually, no, it's 79 cents. You know, it doesn't grow a heck of a lot. It's $500, which isn't a lot either, but it's a little more extra. Now, radioactivity is another place where you're going to see. I forget now, the new curriculum in physics, does it go through radioactivity?
No.
Nope. You guys, who's done physics here?
We haven't, I don't think it's on our,
Stuff, and you'll come across half-life problems in this section. Now, find the half-life of a radioactive substance with a decay equation given as, hey, y equals y, 0, e to the negative kt in this case, because it's shrinking over time. And half-life is when y is equal to half the original amount. That's what you need to know out of this. So, the time, half the original amount. The original amount is y0, we say, right? Okay, so that's just interpreting what the problem's asking. So hey, the calculus part is already done for you. They're saying this is the equation. We want y, the half-life time, so we're going to use when y is half the original amount. Y, I'm going to sub this in for the y value on this equation, right? I'm going to say 1/2 y0 is equal to y0 e to the negative kt. Dig that? What can you do with the y0s? It's just some amount. But it's the same number on both sides, isn't it? What's that? They cancel out, they divide up. So really this becomes, I'm dropping the colors. Oh, divide both sides by y0. Now how do I solve for time in this case? The log of nature. So the natural log of a half is equal to negative kt. Right, I'm skipping the e to the natural log of e to the, because we know that they're inverse functions of each other. I said the right word. Now, t is equal to, well, this divided by k, right? Negative k. Okay, that's an expression. We didn't get any real values for this. So this could be an expression. It's clunky and you won't see it like this, though. You could manipulate this a little bit. What do you know about fractions? Natural log of 1/2. How could you separate that into two things? Sure. Division, remember the rules of exponents apply here. So, what I'm saying here is t is equal to the natural log of 1 minus the natural log of 2. What is the natural log of 1? What's the log base 10 of 1? 0. Ah, yeah. E to the 0 gives me 1. 5 to the 0 gives me 1. So that's what that's asking, the natural log. E to the what gives me 1? 0. So this turns into, on the numerator, 0 minus natural log of 2, right? Over negative k. I'll write that down here, but I wouldn't normally. I'd say, well, 0 minus natural log of 2. You see how the negative signs are going to cancel out? Now, what I circled was just den. But this is probably how you'll see it. You can probably see it as 1 over k. Either way, I'll write it this way. The natural log of 2 over k. And you'll find this in textbooks. Often they'll just have decimal 693, which is the natural log of 2 evaluated, divided by the constant. Well, that doesn't do a lot for me, you're saying? I don't know. I'm going to skip the base change thing right now, and we might come back to it. I'll talk to you about it later. We will play around with this, and then, yeah, carbon dating. And then we'll have this all wrapped up in one class and lots of time to work on these things. Okay, scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the original nuclei have 10% of the radioactive nuclei have decayed. This is how they date fossils and stuff like this of human remains and stuff. So if 10% is decayed, how much is left? 90%, right? That's the important thing to realize, the way it's written. 90% is left. Now, as a decimal fraction, that's decimal 9, right? Decimal 90. So we're going to use the old A equals the amount, 1/2, and then I'm going to use it like this. T 5700. Now, where the heck did this come from, you're probably thinking? This is from thinking about half-lives. Does it make sense if 5,700 years is 1 half-life, right? If I put in, I just made up this function here. So if the time was 5,700, oh, I shouldn't have done that. But if this is 5,700, you'd have an exponent of 1, right? 1 half-life would have occurred. Remember when I was over on the board talking about 100 grams? After 1 half-life, you have 50 grams. So that would just turn into, to the power of 1, half of whatever original amount you had. After 2 half-lives have occurred, so 2 times 5,700, you plug that in here, and you get 2 half-lives occurring. You get 1/2 squared. You have a quarter of whatever the original amount is. That's how I made up the function. Whoa, you're just thinking, what? Anyways, I don't know how much was originally there or what, but I do know that 90% is left. So 0.9 as a decimal percent is equal to the original amount if it was 1. Try to avoid using hundreds and stuff like this. Leads to less error. Now, this is what we got set up here. How do you undo this? Logs. We're going to stick to the natural log always. Because I don't have natural, or I don't have log base half on my calculator. Actually, I think you guys might know this. So I'm going to take the natural log of 0.90 to solve this. The natural log of 1/2 t to the 5,700, t to the t over 5,700 as the exponent. According to the rules of logs, if I have an exponent inside the log, what can you do? Yeah, so this is really just algebra here. There's really not much calculus here. Okay. Now I could just use my calculator and evaluate. I can multiply the 5,700 up, natural log of 9, decimal 9, divided by the natural log of half.
Right.